Post-Newtonian formalism is a calculational tool that expresses Einstein's equations of gravity in terms of the lowest-order deviations from Newton's law of universal gravitation. This allows approximations to Einstein's equations to be made in the case of weak fields. Higher-order terms can be added to increase accuracy, but for strong fields sometimes it is preferable to solve the complete equations numerically. Some of these post-Newtonian approximations are expansions in a small parameter, which is the ratio of the velocity of the matter forming the gravitational field to the speed of light, which in this case is better called the speed of gravity. In the limit, when the fundamental speed of gravity becomes infinite, the post-Newtonian expansion reduces to Newton's law of gravity. The parameterized post-Newtonian formalism or Ppn formalism is a version of this formulation that explicitly details the parameters in which a general theory of gravity can differ from Newtonian gravity. It is used as a tool to compare Newtonian and Einsteinian gravity in the limit in which the gravitational field is weak and generated by objects moving slowly compared to the speed of light. In general, Ppn formalism can be applied to all metric theories of gravitation in which all bodies satisfy the Einstein equivalence principle. The speed of light remains constant in Ppn formalism, and it assumes that the metric tensor is always symmetric. History. The earliest parameterizations of the post-Newtonian approximation were performed by Sir Arthur Stanley Eddington in 1922. However, they dealt solely with the vacuum gravitational field outside an isolated spherical body. Dr. Ken Nordtvedt expanded this to include 7 parameters. Clifford Martin will introduce a stress, continuous matter description of celestial bodies. The versions described here are based on Way-to-Ni, Will and Nordtvedt, Charles W. Misner et al., and will and have 10 parameters. Beta-delta notation. 10 post-Newtonian parameters completely characterize the weak field behavior of the theory. The formalism has been a valuable tool in tests of general relativity. In the notation of Will, Ni and Misner et al., they have the following values. Is the 4x4 symmetric metric tensor and indexes and go from 1 to 3. In Einstein's theory, the values of these parameters are chosen to fit Newton's law of gravity in the limit of velocities and mass approaching zero, to ensure conservation of energy, mass, momentum, and angular momentum, and to make the equations independent of the reference frame. In this notation, general relativity has Ppn parameters and alpha-zeta notation. In the more recent notation of Will and Nordtvedt and Will, a different set of 10 Ppn parameters is used. Is calculated from the meaning of these is that, and measure the extent of preferred frame effects, and measure the failure of conservation of energy, momentum and angular momentum. In this notation, general relativity has Ppn parameters, and the mathematical relationship between the metric potentials and Ppn parameters for this notation is, where repeated indexes are summed, is on the order of potentials such as the square magnitude of the coordinate velocities of matter, etc. Is the velocity vector of the Ppn coordinate system relative to the mean rest frame of the universe. Is the square magnitude of that velocity, if and only if, otherwise. There are 10 metric potentials, and 1 for each Ppn parameter to ensure a unique solution. 10 linear equations in 10 unknowns are solved by inverting a 10 by 10 matrix. These metric potentials have forms such as, which is simply another way of writing the Newtonian gravitational potential, where is the density of rest mass, is the internal energy per unit rest mass, is the pressure as measured in a local freely falling frame momentarily commoving with the matter, and is the coordinate velocity of the matter. Stress energy tensor for a perfect fluid takes form. How to apply Ppn. Examples of the process of applying Ppn formalism to alternative theories of gravity can be found in Will. It is a 9-step process. Step 1. Identify the variables, which may include dynamical gravitational variables such as the metric, scalar field, vector field, tensor field and so on, prior geometrical variables such as a flat background metric, cosmic time function, and so on, matter and non-gravitational field variables. Step 2. Set the cosmological boundary conditions. Assume a homogeneous isotropic cosmology, with isotropic coordinates in the rest frame of the universe. A complete cosmological solution may or may not be needed. Call the results. Step 3. Get new variables from, with, or if needed. Step 4. Substitute these forms into the field equations, keeping only such terms as are necessary to obtain the final consistent solution for. Substitute the perfect fluid stress tensor for the matter sources. Step 5. Solve for 2. Assuming this tends to 0 far from the system, one obtains the form whereas the Newtonian gravitational potential and may be a complicated function including the gravitational constant. The Newtonian metric has the form. Work in units where the gravitational constant, measured today far from gravitating matter, is unity, so set. Step 6. From linearized versions of the field equations, solve for 2 and 2. Step 7. Solve for 2. This is the messiest step, involving all the nonlinearities in the field equations. The stress-energy tensor must also be expanded to sufficient order. Step 8. Convert a local quasi-Cartesian coordinates into standard Ppn gauge. Step 9. By comparing the result for with the equations presented in Ppn with alpha-zeta parameters, read off the Ppn parameter values. Comparisons between theories of gravity. A table comparing Ppn parameters for 23 theories of gravity can be found in Alternatives to General Relativity #Ppn parameters for a range of theories. Most metric theories of gravity can be lumped into categories. Scalar theories of gravitation include conformally flat theories and stratified theories with time orthogonal space slices. In conformally flat theories such as Nordström's theory of gravitation, the metric is given by n for this metric, which violently disagrees with observations. In stratified theories such as Yilmaz's theory of gravitation, the metric is given by n for this metric, which also disagrees violently with observations. Another class of theories is the quasi-linear theories such as Whitehead's theory of gravitation. For these, the relative magnitudes of the harmonics of the Earth's tides depend on them, and measurements show that quasi-linear theories disagree with observations of Earth's tides. Another class of metric theories is the biometric theory. For all of these is non-zero. From the precession of the solar spin we know that, and that effectively rules out biometric theories. Another class of metric theories is the scalar tensor theories, such as Brandsteder theory. For all of these, the limit of means that would have to be very large, so these theories are looking less and less likely as experimental accuracy improves. The final main class of metric theories is the vector tensor theories. For all of these, the gravitational constant varies with time and is non-zero. Lunar laser ranging experiments tightly constrain the variation of the gravitational constant with time, and so these theories are also looking unlikely. There are some metric theories of gravity that do not fit into the above categories, but they have similar problems. Accuracy from experimental tests. Bounds on the Ppn parameters will cm is momentum conserved. A test in the binary system PSR 1913/16, Astrophysical Journal, Part 2 Letters, Volume 393, No. 2, July 10, 1992, L59L61. Based on from will, it is theoretically possible for an alternative model of gravity to bypass this bound, in which case the bound is from Ni.